Okay, let's unpack this. We are moving, I think, decisively past the simple list of tools you could use. And we're plunging straight into the how, and I think most critically, the underlying architectural logic of system design.
Right. The why.
Exactly, the why. Specifically, we're looking at cloud data pipelines today. This deep dive is really for you if you already know the names of the services, but you really want to master the art of connecting them efficiently and robustly.
What's fascinating here is that the correct solution, especially at this level, isn't just about getting it to work. I mean, anyone can make data move from point A to point B eventually.
Sure.
The real architectural mastery, and this is especially true at this intermediate stage we're talking about, is all about optimization. It's about scalability, and it's about connecting the right purpose-built tools for the right job.
Which, in the long run, saves you massive amounts of money and maintenance time.
Oh, huge amounts. The two scenarios we're tackling today are perfect examples of this. They highlight these core decisions that, professionals are facing every single day when they're trying to build reliable, high-performance, and, just as you said, cost-effective systems.
Absolutely. So our mission today is a deep dive into what we're calling an intermediate solution workshop.
I like that.
We're going to be dissecting two very distinct, but I think equally challenging scenarios from our source material. And they force us to consider both technical performance on one hand and financial accountability on the other.
A classic tension.
It is. The first challenge is all about operational scale. How do you turn these high-volume, continuously generating operational logs into a dashboard that's actually functional and aggregated?
Right.
And the second challenge pivots completely to finance. It's about establishing reliable, accurate attribution and tracking of costs across multiple separate systems that, and this is the key, just happen to be living inside a single shared cloud project.
And here's the promise we want to make to you, the learner. We're not just going to present the optimal solution and then, move on.
Right.
We're going to dissect the logic behind that choice. And, crucially, we're going to spend a good amount of time analyzing why the alternative, the ones that seem plausible on the surface, why they actually fail.
We're really aiming for those fundamental aha moments, aren't we?
That's the goal. Understanding which tool is truly optimized for which specific constraint and what the real-world maintenance and cost penalties are when you pick the wrong component for the job.
Okay, let's start with data scenario number one.
Yeah.
This is just a foundational challenge in infrastructure monitoring. Our source data is high-volume virtual machine utilization logs. So VM logs.
Right.
These logs are currently being managed and stored within the native Google Cloud Operations Suite, or Ops Suite. So that's our starting line. That's our primary source of the data.
The requirements for the final output, though, that's what truly dictates the architecture here. And they present this unique tension. We need a dashboard that is, 1, highly interactive, 2, easily shareable with business stakeholders, and 3, this is important, updated in what the business is going to call real time.
So fresh data.
Very fresh data. But here's the real constraint. The one that, frankly, eliminates several of the easy-sounding solutions.
What's that?
The need for the dashboard to provide data aggregated across extensive time windows, specifically on a quarterly basis.
How?
That combination, the need for immediate visibility married to the immense power you need to crunch 3 months or more of dense VM utilization logs, that's the core architectural puzzle we have to solve here. And only using Google Cloud Platform solutions.
So we have to balance the speed required for those fresh data updates, with the sheer immense processing power that's needed to perform these heavy analytical queries against these huge historical data sets.
Exactly.
This sounds like a job for, well, the canonical cloud data warehouse pattern. So what's the optimal workflow that achieves this balance elegantly?
The optimal solution, which we're calling option A, is the most robust and, as you said, elegant way to meet all of these conflicting requirements. It's a 3-step pipeline.
Okay.
And it's designed to separate processing, storage, and visualization into their appropriate best-in-class components.
Let's walk through those steps then.
So first, you configure the native export functionality to pipe the VM utilization logs from Ops Suite directly into BigQuery. That is your analytical data storage destination.
Step 1, get the data into BigQuery.
Step 1. Step 2, you create the visualization layer in Looker Studio, and you connect the dashboard canvas directly to that BigQuery dataset.
And step 3.
Step 3, you share the Looker Studio dashboard link with your stakeholders. Done.
It sounds deceptively simple. I mean, a 3-step dance.
Yeah.
But the architectural logic here is so sound because it delegates the heavy lifting to the correct, purpose-built tools. Let's dissect BigQuery's pivotal role here first. Why is BigQuery the non-negotiable component for this specific requirement?
BigQuery isn't just a database. That's the first thing to understand. It is the massive parallel processing engine that we need for this job.
Okay.
It's fundamentally designed for handling massive petabyte-scale data sets, which, operational logs very quickly become.
Oh, absolutely. They grow incredibly fast.
Incredibly fast. And more importantly, it's optimized for performing complex, resource-intensive analytical aggregations. So when the requirement is a quarterly roll-up of utilization across, I don't know, maybe thousands of individual VMs,
Right.
you're talking about queries that need to scan and summarize billions, maybe trillions of log entries. You need the infrastructure of a cloud data warehouse like BigQuery to execute these deep, complex aggregation queries efficiently, quickly, and at a predictable cost.
I want to focus on that aggregation piece for a moment because
Yes.
that feels like the real technical differentiator here.
It is.
If you were trying to do this kind of analysis in let's say, a traditional relational database, that quarterly query would just crush your system or would take hours, maybe days to run.
It would time out.
So how does BigQuery handle that massive analytical load so efficiently?
It's all about an architecture that's designed for scale out rather than scale up.
Okay, what does that mean?
It means BigQuery automatically leverages concepts like columnar storage, massive parallelism, and really sophisticated indexing techniques like partitioning and clustering.
Right.
For utilization logs, partitioning by date, which is the very nature of an incoming log stream, it allows the system to physically segregate the data into smaller, indexed chunks.
So it doesn't have to look at everything all at once.
Exactly. When that quarterly query runs, it doesn't scan the entire historical log history from the beginning of time. It only scans the relevant partitions for the last 3 months, and that dramatically reduces the I/O and the processing time.
And that speed is what lets you meet that real-time expectation, even for historical analysis.
It's the only way. It's the only way to balance that high volume with low latency aggregation.
Okay, so BigQuery has done all the heavy lifting. Now Looker Studio takes over. It provides the front end, the interactive, easily shareable part. Is Looker Studio the right choice just because it's a native GCP tool?
That's part of it, for sure. But the main reason is its specialized function and that native integration efficiency.
Okay.
Looker Studio is purpose-built for business intelligence visualization. It connects natively and, more importantly, efficiently to the high-performance analytical engine of BigQuery.
So it's not pulling data out and processing it separately?
No, it doesn't need to pull massive amounts of data into some local memory cache or a separate analytical layer. It queries BigQuery directly. And crucially, that real-time update requirement is met because when a user opens the dashboard or even just hits refresh, Looker Studio executes a fresh SQL query against the highly optimized, fresh data that's already sitting in the data warehouse. This pairing high-scale storage calculation combined with low-latency dedicated visualization, this is the battle-tested blueprint for operational reporting at scale.
Okay, that's the gold standard, the canonical pattern. But as we promised, we often learn the most by dissecting the failures.
Right.
So let's look at the suboptimal alternatives and analyze precisely why they introduce these fatal flaws or cost bottlenecks or just maintenance nightmares into the system. Let's start with option C. I think this is the most tempting one for smaller teams, or maybe those just relying on familiar Office tools. We're calling it the Google Sheets trap.
The trap. Yes.
The proposed workflow is opt suite to BigQuery, so far so good, but then a CSV export into Google Sheets and then a Google Sheets dashboard.
Oh, boy.
It looks like we're using BigQuery for the initial crunch, so we're sort of halfway there. But why introduce that manual, messy middle step of a CSV in Sheets, and where does this architecture just completely break down?
This choice is a classic mistake, and it's rooted in comfort, familiarity rather than in technical fitness for the job.
Right. People know Sheets.
Exactly. People propose it because Sheets is familiar, it's easy for collaboration, and it's seemingly free. But when we analyze the requirements, massive scale and quarterly log aggregation, the architectural flaw becomes not just obvious, it becomes, frankly, catastrophic.
Okay, so where's the first breakpoint?
So while the initial step of putting the data into BigQuery is correct, the mistake is that immediate next step, forcing that high-volume, aggregated log data into Google Sheets. Sheets introduces hard, immovable limits on data volume. And while those limits might seem high on paper, millions of cells,
Right.
a quarterly aggregation of continuously generated VM logs from even a moderate infrastructure will rapidly exceed the practical limits of what Sheets is designed to manage or process or even query responsively. Sheets is for manageable, structured data like financial ledgers. It simply cannot handle the sheer continuous growth and the query load required for a large-scale historical utilization dashboard.
So performance degradation is one major failure point. But what about the real-time requirement? That seems to be completely shattered by this manual data transfer step.
It absolutely shatters it. It's not just degraded, it's gone. The workflow dictates manual steps, exporting a CSV from BigQuery and then manually importing that file into Sheets.
Right. A person has to do that.
A person has to do that. This introduces massive, unpredictable latency and completely violates the principle of automation. You move from a continuous pipeline where data is available almost instantly to a manual process bottleneck that needs human intervention every single time you want the data updated.
So if the business is asking for real-time updates or even hourly updates,
you can't do it. This process is, at best, a daily process. Or, as I once saw, it's a process that only happens every Tuesday at 10 a.m., which leads to stale data that everyone mistakenly believes is current. It's not scalable, it's not continuous, and it's certainly not reliable.
that's the Sheets trap in action, sacrificing architecture for familiarity. Okay, excellent. Now let's move to option D, the custom application bottleneck.
Ah, yes.
The workflow here was ops suite to a cloud storage bucket, then using the cloud storage API to a custom application, which then powers a custom dashboard. Now, wait a second. If my company already has strong front-end and full-stack developers, isn't it actually cheaper and faster to just build this thing in-house? Rather than paying perpetual Looker licensing or query fees, why would we not want to build a custom solution for maximum control?
That is the temptation. And that is precisely where architects earn their salaries, by understanding the true total cost of ownership, the TCO.
Right.
Building a custom solution is often the most expensive default answer, architecturally speaking, when a dedicated managed service already exists. The goal, remember, was to deliver an interactive, easily shareable dashboard efficiently.
Okay.
Looker Studio, which we use in Option A, is a mature, out-of-the-box solution specifically designed for high-performance visualization and data governance.
But what are the hidden costs in the custom app route?
Option D requires you to develop, secure, scale, and maintain the entire visualization and query layer yourself. That's steps 2, 3, and 4. Think about the hidden costs. You have to write and maintain the logic to authenticate users, manage authorization levels, query the underlying data, which is now in a storage bucket and has to be retrieved via an API, then render the charts, and then manage the entire web application infrastructure, the servers, the load balancers, deployment pipelines, security patching.
Every single bug fix.
Every single bug fix, every browser update, every security vulnerability now falls squarely on your development team.
That sounds like a massive drain on resources that, frankly, should be focused on core business logic. It's a huge opportunity cost.
Exactly. It's the opportunity cost of having your developers build a bespoke version of a business intelligence tool instead of focusing on the core product features that actually generate revenue or give you a competitive advantage. And beyond that, the operational overhead is severe. You've replaced a zero-maintenance managed visualization service with an entire production application stack. The maintenance burden and the true TCO, when you factor in developer salaries, infrastructure costs, and security compliance, are orders of magnitude higher than just using a managed BI tool designed for this.
So the principle is use managed services where you can.
Absolutely. The principle of efficiency in cloud architecture demands it. It minimizes this kind of architectural overhead.
That brings us to our last bad option, option B. I think this one is a misapplication of purpose-built tools. We're calling it the SIM misalignment. The workflow was ops suite to cloud PubSub, then to a SIM system, which powers a SIM dashboard. Now, PubSub is a great messaging layer, and SIMs handle logs. So on the surface, this doesn't sound crazy. Why is this pipeline wrong for this specific utilization dashboard?
This one fails because the architecture routes the data stream to a tool that is fundamentally optimized for a different type of query, and that leads to massive inefficiency and expense for the outcome we want.
Okay, let's start with PubSub. Why is that a problem here?
Well, while it's excellent for handling high volumes of incoming streams asynchronously, adding it here just complicates the pipeline. You're adding a durable message queue where one isn't strictly necessary for a BigQuery export. It just introduces an extra layer of cost and management overhead for no real benefit in this case.
And the primary failure is the SIEM system itself.
Precisely. SIEM, that's Security Information and Event Management Systems, are purpose-built for security analysis, for real-time alerting on threats, forensic investigation, compliance tracking.
Right.
Their internal database structure, their indexing, it's all optimized for rapid, narrow searches. Things like looking for a specific IP addresses activity over the last hour, or a single login failure pattern. They are terrible and terribly expensive at doing wide, deep analytical aggregations. So routing general infrastructure utilization logs data we need to aggregate quarterly into an index that's optimized for security means that our quarterly aggregation query will be slow, it will be resource intensive, and it will be extremely costly because you are forcing a tool to do a job it was never ever meant to do. Furthermore, the dashboard and the interface will be optimized for security analysts, which makes the data less accessible and frankly less useful for the business stakeholders who only care about utilization trends and capacity planning. They don't need to see firewall logs.
So we're basically using a surgical scalpel, the SIEM, which is optimized for that forensic detail, to perform a task that really requires a large industrial excavator, which is BigQuery, optimized for massive aggregation.
That's a perfect analogy. The tool is fundamentally mismatched, both technically and financially, for general business reporting.
And so, in summary, option A maximizes efficiency by matching BigQuery's exceptional aggregation power with Looker Studio's visualization simplicity.
This combination minimizes your architectural overhead, it satisfies both the immense scale and the low latency timing requirements, and it ensures the data is easily accessible to the correct audience. It just works.
Now we switch gears entirely. We're moving from the realm of technical performance and log analysis to high-stakes financial accountability.
The money.
The money. And this is often where architectural mistakes become the most expensive and frankly create the most organizational friction. Because finance teams, they demand accuracy. They demand auditability.
And they should.
This second scenario presents a universally common and critically important problem. You're managing several distinct production systems. Maybe they're running different microservices or applications, all on dedicated compute engine instances.
Okay.
But crucially, they are all running within the same GCP project. They share the same billing container.
That's the tricky part, the shared project.
Exactly. The goal is crystal clear.
Yeah.
We cannot just look at the total project cost. We need to know precisely how much it costs to run each of those distinct systems. System A, System B, and so on.
You need granular financial attribution, chargebacks.
Yes, for accurate chargebacks. This requires reliable, auditable segmentation of what is essentially a shared pool of costs. Let's outline the optimal methodology. This is option B, which is the architecturally sound answer for enterprise financial attribution.
The optimal workflow dictates 3 steps that really leverage the native platform features. First, you must assign all the resources, in this case the compute engine instances, a uniform label that's specific to the system they support.
So a system, a label, for example.
Exactly, a key value pair. Second, you configure the native BigQuery billing export feature.
Okay.
And third, you query the granular costs segmented per label directly in BigQuery.
This sounds straightforward, but we really need to explain why labels are the only proper technical answer here. Why can't we just rely on, say, the VM name or some other attribute?
Because labels are the feature that was designed from the ground up to solve this exact problem, and they integrate directly into the financial ledger of the platform.
What do you mean by that?
Labels are standardized key value pairs. They were designed specifically by the cloud providers for grouping and organizing cloud resources, not just for operational management, but critically for billing, for automation, and for policy application across the entire platform.
Okay.
The critical step is that billing export to BigQuery. When you configure this, GCP creates this granular, denormalized financial data set. And the essential architectural knowledge nugget is this. The export process automatically includes the applied resource labels as dedicated fields right there in the billing data schema.
Oh, wow. So it's a first-class citizen in the data itself.
It is a first-class citizen. This direct first-class integration means you can run simple, highly powerful SQL queries within BigQuery to effortlessly break down charges by system, by environment, or by any label you've defined.
So the label isn't just some organizational tag sitting on the VM. It's more like an integrated foreign key that automatically gets mapped to every line item, every single dollar spent by that specific resource within the financial data itself.
That's a perfect way to put it. That direct system-managed link is the architectural necessity. It provides the required auditable structure to link your technical spend back to a defined business unit or a system.
Yeah.
If you try to achieve granular cost attribution without using labels, you are fundamentally fighting the platform's native cost reporting structure. And that inevitably leads to complex, fragile, and very expensive workarounds.
And this also gets at the bigger question of why separating this cost data is so critical in the first place.
It does. Financial accountability, accurate chargebacks, they require a dedicated, consistent, and auditable structure that works universally across all your resource types, not just your VMs. Labels provide that structure, and they ensure that the finance team trusts the data, and the engineering team can easily understand where the money is actually going.
Okay, so let's look at why these simpler or seemingly similar alternatives fall fundamentally short here. Starting with option A, the simple console view trap. The workflow suggests just use the cost breakdown section in the GCP console to visualize costs per system. I mean, the feature's literally called cost breakdown. Why can't we just use the built-in view? Isn't that what it's for?
It is excellent for basic cost viewing, but it lacks the necessary granularity that our specific problem statement requires.
Right.
The standard cost breakdown section in the console is fantastic for high-level aggregated views. It can show you your total costs per service, like the overall spend on a compute engine, or it can show you the total cost separation between Project X and Project Y.
But that's not our problem.
That is not our problem. Our problem specifies that multiple distinct systems, System A and System B, are running within the same project and they are using the same service compute engine. The console view does not provide an easy user-defined mechanism to slice that shared compute engine cost between System A and System B.
Unless they're separated, which they are not.
Which they are not. It doesn't allow for segmentation based on custom user-defined attributes like the name of the production system.
So just to be clear, if I have 3 VMs for System A, and 3 VMs for System B, and they're all standard compute engine instances in the same project, the console will only tell me the total cost of all 6 of those VMs combined.
Precisely. You need the unparalleled flexibility of BigQuery SQL, combined with that label mapping, which acts like a fine-toothed comb, to perform that custom slice and dice across the shared pool of compute engine spend. The console is useful for project-level separation. BigQuery export plus labels is necessary for intra-project service-level attribution.
Got it. Okay, next let's tackle option C. Now this, as an engineer, is the most deceptively plausible alternative because metadata is so easy to work with operationally.
Yes, very tempting.
This is the metadata misuse. The workflow suggests enrich your instances with metadata, then configure cloud logging to export to BigQuery, and then query costs based on the metadata. What is the fundamental unforgiving difference between metadata and labels when it comes to the money?
This is such a critical distinction, and it really exposes the difference between operational knowledge and financial governance. Metadata and labels, they are both key value pairs.
Right, they look the same.
They look the same on the surface, but they serve fundamentally different purposes, and they integrate into the platform in entirely different ways.
Okay, let's break that down. What's metadata's role?
Metadata's role is strictly operational. It's for configuration management and runtime logic. For instance, a service might read its own metadata tag to find a database connection string. It's information that machines read and act upon.
And labels.
Labels' role is primarily financial and organizational. It's information that humans and reporting systems rely on for grouping and for accountability.
So what's the technical failure point here? Why can't we make it work with metadata?
The critical failure point in option C is simple. Metadata is not natively included in the standard BigQuery billing export data stream. Labels are. The billing data only contains the technical charge information linked to the resource ID and any associated labels. It consciously omits operational metadata, and that's by design. It keeps the financial ledger clean and focused.
So to achieve the goal using metadata, you were forced to create a really complex, expensive architectural workaround. What does that workaround even look like, and why is it so fragile?
It creates a massive architectural burden. You would be forced to correlate the official auditable billing export data in BigQuery with a separate, massive, and continuously flowing stream of operational log data exported from cloud logging.
Okay.
That's the stream that does contain the metadata. So this correlation requires you to run a complex, resource-intensive, and inherently fragile join operation across two distinct, potentially gargantuan data sets: the financial ledger and the operational log stream.
And that sounds expensive and slow.
It's both. The fragility comes from several factors. First, cost. Running repetitive, massive joins across two tables that weren't designed to be joined in BigQuery is costly and slow. Second, consistency. Billing data flows on a different schedule and has a different schema than operational logs. You risk latency issues, consistency problems, when you're trying to correlate data where the schemas might drift or the logging granularity doesn't perfectly match the billing granularity.
So you're basically guessing.
You're using an operational attribute, metadata, to infer a financial fact, which is just unreliable. Labels, by contrast, eliminate this fragility entirely by being baked into the core financial data structure from the start.
That makes the complexity and the maintenance costs of option C prohibitive compared to the simplicity and native integration of option B. Okay, one last alternative, option D. The naming convention flaw. The workflow suggests name each virtual machine, each VM, after the system it runs. Then set up a usage report export to cloud storage. Configure that bucket as a source in BigQuery to query costs based on the VM name. A VM name is specific. Why is this less robust than a label?
This is a pragmatic, immediate fix that ultimately fails due to a lack of universality and long-term maintenance issues.
Okay.
The primary and most critical issue is scope limitation. VM names, by definition, only apply to compute engine instances. This solution completely breaks down the moment your System A is not just running on a VM.
Right. Real systems are more complex than that.
Oh, of course they are. Consider the reality. If System A uses compute engine VMs, a Cloud SQL database instance, a dedicated load balancer, and several cloud storage buckets, how do you reliably and consistently attribute the network, the database, and the storage costs using a VM naming convention?
You can't.
You can't. Those other resources won't share the VM name. This leads to incomplete, inaccurate cost attribution where the database charges, which might be significant, are just ignored or lumped into some unattributed bucket.
So the naming convention only solves the compute engine part of the problem, not the holistic system cost problem.
Exactly. Labels, conversely, can be consistently applied across nearly all resource types: VMs, databases, storage buckets, network components, managed services. They provide a unified, holistic cost view for the entire system, regardless of which underlying service is being consumed.
And there's a maintenance issue too,
A
right?
huge one. The second major failure is maintenance and technical debt. Relying on parsing names within your production BigQuery queries requires string manipulation, often involving complex regular expressions or rejects or brittle-like clauses.
Ugh.
Yeah. And if your naming convention changes slightly, say you move from System A prod VM01 to say production instance 01, all of those complex string-reliant SQL queries break immediately.
Right, and they will change.
They always do. Labels are standardized key-value pairs, which makes the queries far cleaner, immune to minor naming changes, and dramatically easier to maintain over the long term. Option B just maximizes consistency, auditability, and reliability across your entire resource portfolio, which is paramount when you're dealing with financial data.
So let's zoom out for a second and consider what we've learned from these two wildly different architectural challenges. In part one, we were analyzing high-volume, potentially unstructured systems performance logs, pure technical data. In part two, we dealt with sensitive, highly structured financial data, the dollars and cents of accountability.
Two very different worlds.
But there is a massive unifying pattern here that I think really defines modern cloud analytics.
This pattern is the key architectural insight for any intermediate cloud professional, and it revolves entirely around the versatility and the unique capabilities of the cloud data warehouse.
Okay.
The crucial realization is that BigQuery functions as the non-negotiable central analytical hub for both disparate, technical, and high-stakes financial data.
It's the common denominator. The Swiss Army knife for complexity.
Let's put it into context. In scenario one, BigQuery successfully ingested high-volume, continuous, real-time operational logs from Ops Suite, and it enabled heavy, quarterly technical aggregation for utilization reporting. It handled the massive streaming influx and the demanding calculation workload you need for historical analysis.
And then completely differently in scenario two, BigQuery ingested crucial, highly structured financial data directly from the platform's native billing export mechanism.
Right.
And here, it enabled fine-grained cost attribution and auditable reporting based on external resource definitions, the labels.
The core conclusion here is about BigQuery's unique architectural advantage. Its scale-out architecture allows it to handle these vast, complex, multi-petabyte data sets, but the key feature is its capacity to handle both structured data, like financial ledgers, and semi-structured data, like machine logs, in the same place. This versatility makes it the logical, centralized destination for virtually all disparate data streams that require complex, deep analytical processing. It doesn't matter if the source is a simple machine log or a regulated financial ledger.
And this convergence, having both technical and financial data in one massive performant hub, that's the foundation for much more advanced architectural thinking, isn't it?
It fundamentally defines the architecture of modern cloud analytics, and it does it by enforcing a clean separation of concerns, which we saw in the failures of all the suboptimal options.
Right.
We avoid creating these complex point-to-point integrations, and instead we rely on three simple, distinct layers. First, data ingestion and preparation. Specialized systems handle this. Ops Suite for logs, billing export for financial transactions. They are highly efficient at their specific job.
Then the second layer.
Data storage and sophisticated querying. This is the centralized analytical function handled by BigQuery.
And finally,
Visualization and presentation. The front-end function handled by dedicated BI tools like Looker Studio.
I think the biggest takeaway for our intermediate listener, tying back to the failures in both Part 1 and Part 2, is that success comes from leveraging the platform's native integrations. Every single suboptimal solution involved fighting the native flow or trying to recreate a managed service.
That's a critical synthesis. Efficiency is achieved by integrating with the platform where it provides a dedicated feature. When we used labels in Scenario 2, we were leveraging a feature that is natively integrated into the billing export schema. When we used Looker Studio, we leveraged a tool natively integrated with BigQuery.
Right.
Any attempt to bypass these native, high-performance governed features, like trying to correlate metadata logs or relying on manual CSV exports, it just introduces unnecessary technical debt, cost, and fragility. The most efficient architecture is the one that minimizes steps and leverages the platform's baked-in organizational and analytical capabilities.
That truly brings us to the end of a deep and, I think, very intricate dive into intermediate architectural logic. We've covered some crucial ground today. We mastered the importance of pairing BigQuery's immense scale and query power with Looker Studio's dedicated interface to handle dashboards requiring massive long-term aggregation. And we drilled down into the non-negotiable role of labels for accurate, auditable financial attribution, especially within those shared cloud projects where costs are so often commingled.
The primary lesson here for you, the learner, remains that architectural fitness is really synonymous with maximum efficiency and minimum complexity. Every correct choice we analyzed, using labels, using Looker Studio, using BigQuery, was the choice that minimized custom steps and maximized consistency across the platform.
You have to use the dedicated tool for the job.
You must always use the dedicated attribute or the managed service that is optimized for the specific task at hand.
It's all about designing for robustness, auditability, and minimizing human intervention and technical debt.
Absolutely. And as we finish up this solution workshop, we want to leave you with one final provocative thought. A concept that builds on the power of this unified data hub we've been talking about.
Okay, let's hear it.
If BigQuery is now the centralized source for both your operational utilization data from Scenario 1 and your raw financial cost attribution data from Scenario 2, how could we design a third proactive system? Think about creating a predictive financial model. This system would use the aggregated historical utilization data, the history of how much capacity was used, and merge it with the cost attribution data to automatically and accurately forecast future costs.
So using today's logs to predict tomorrow's bill.
Exactly. Leveraging these two independent data streams, now that they're co-located and standardized in BigQuery, to create a forward-looking predictive financial model is perhaps the next critical level of architectural thinking.